Now it's very easy to introduce Jean-Marie Lehn because we have been speaking about him in our presentation, and everybody knows Jean-Marie Lehn, and he doesn't need any introduction at all. He's the pioneer in supramolecular chemistry. He's the conceptual father of this discipline, and he has a brilliant and extraordinary career. He was awarded in 1987 with the Nobel Prize of Chemistry, and it's a big honor to have here today with us. So please, Jean-Marie, the stage is yours.
So it's a pleasure to be here. I'm València every year, but not the COVID years. So last time was 2000, what was it again? 19, I think. So it's a pleasure to be also to have this occasion to talk at this meeting, which combines two things. As you see here, the 125th anniversary of studies in chemistry at the University of València and the International Symposium of Metal Complexes. I would like to point out also that thank you for your lecture you were giving, and in order to help the Ukrainian scientists, they are now organizing Kharkiv seminars in chemistry, and they're giving 4 hours lectures in the week of 13 and 14, and of 13 and 14th of June. So, this being said, I selected something which had to do with metal complexes, but metal complexes in our work were also very important, not so much for for some reasons as metal complexes, but also for driving a system. Metal-ion coordination can drive a system for a given evolution. And that is why I call it also metal complexes with a purpose. The metal complexes are used for a reason, as you will see, and not just because they are metal complexes. Okay, so as you know, molecular chemistry is isolated molecules. When you put them together, you get supramolecular chemistry, and once this is understood better, then one comes to the self-organization. That means the possibility of the systems to undergo an organization driven by some type of interactions. One of those, which we are concerned about, is a metal complex. And we have, like many others, started many years ago now to try to make metallo-supramolecular architectures of different types by using designed ligands and given metal complexes. First, I show you some examples of that, and then we will look into it a little bit more carefully. For instance, one can make helical substances, double helices and triple helices. This double helix is a double helix which we will see in a moment with copper ions, copper 1, and the chain of and a synthetic molecular chain, and that's a triple helix with nickel. One can make grid complexes where the metal ions connect ligands together and maintain them in a perpendicular way, so that at each intersection there is a metal ion which stabilizes the entity. That's a circular complex where the metal ion drives the system to form, in fact, the circular helicate. It's double helices, but in a circle, like a plasmid in a bacteria. And this is a case where one has, this is old work, but it's a case which illustrates well the fact that if you have linear molecules, flat molecules, and if they are designed the right way with metal ions again, they assemble and give only that structure. Now, what are they useful for? This is just an illustration, and many other things have been done by many groups around the world. Now, this self-organization is of course interesting for different reasons, also for having specific properties which are due to the organization of the structures, but also to the metal ions which are present. Now, how can metal complexes then direct the system? Initially, the first case was the one we had done many years ago now, to try to make double helices and triple helices. And helicates are these entities which have helical shape and which are based on a designed ligand and using the correct middle ion to bring them together. Double helices can be formed by using linear chains of bipyridenes and copper-1. Copper-1 has a tetrahedral coordination, so it puts the ligands this way, which means that they have several done in a row, they turn and make a double helix. Triple helices can be then obtained by using middle ions which have octa coordination, and which then have the ligand is somewhat different for reasons which are quite obvious. That if you put substituents, if you put the connections in alpha position, they bump into each other, so they cannot form helices which have octahedral centers. And here with nickel, but it works also with cobalt, it works with iron, all the middle ions which form octahedral coordination, and then you get a triple helix. So that was designed, that was wanted in that way, and it works. The previous slide showed some other examples. Now, then several different approaches were used to demonstrate that you can design, but you can also use middle complexes to drive the system to operate a selection. This was done in the following way. By mixing the ligands which give a double helix with the ligands which give a triple helix, together with copper-1 and together with nickel. So it's a mixture. You just mix it and you let it go. And the system knows, so to say, how to assemble. This is the unit which gives a double helix with copper-1. These are those which give a triple helix with nickel-2. And when you mix them, they automatically go to the generation of a double helix and of a triple helix. No mistakes, because the design is sufficient and the binding is strong enough to drive the system to make only this, which means there is a sort of a self-recognition. The system recognizes the right pieces so as to form the correct double helix and the correct triple helix. As you can see, it's not recent, but it was a way, because it introduced things for us to a direction, driving a direction. Now, the other interesting point, and this was very important for the work we are now doing, was that when you use this ligand with iron and let it just interact, you get this very nice cyclic circular helicate. Now, the cyclic circular helicate, one could obtain the crystal structure, and one finds that there is a chloride in the middle. So, you can say, I'm happy with it, I get this nice compound, and that's it, and do something else. But like often in science, and in chemistry in particular, the experiment wants to tell you something else, and you have to be very attentive. You know, this happens often when we work for something. We have a goal, but that goal is interesting, but maybe there is something behind that which is more important. And here, what was more important is the following. This is the crystal structure, which just shows that it is correct, but otherwise it was not so easy to prove. But with the crystal structure, there is no discussion anymore. And then when you now replace chloride, because chloride was here, and the idea, I thought that the reason why this thing makes this nice circular helicate is that the chloride in the middle is strongly bound in 5 times 2 in 10 plus charges, because there are 5 irons. So it's the thermodynamics of the attraction between 10 plus and 1 minus, which makes this system. And indeed, when you use something which cannot penetrate in the cavity, like sulfate, then you get a hexagon and not a pentagon. Okay? As I show here. And when you add chloride to this hexagon, you go back to the pentagon. And if you remove the chloride, you go back to the hexagon. What does that mean? That means that you have a system which can, in principle, produce a square, a pentagon, or a hexagon, depending on what you use. The square I cannot show you because I have another slide, but I didn't put it in. So that means that it's a dynamic set of possible structures which can be interchanged. And what happens depends on what conditions you use. So you have an adaptation to what is going on. You have an adaptation to what is present. And out of this came all our work then of adaptive chemistry, which we are now mostly doing. So it was really this experiment which inspired the fact that there are systems where you can interconvert the entities, metal ions, that means interconverting different complexes, and what you obtain, that means the system adapts to what is present. And if you change that, the system will do something else. And this then this means that you can design your systems, and many have been designed. The ones I showed you on the second slide, like many people around the world have made metallo-supramolecular architectures, also in València, with a design intention, where you put information, the way you design your ligands, and you can have a program which then, when it runs, generates the final metallo-supramolecular architecture. The next step in complexity is to let the system choose what it wants, not to have you to impose it. You let it go. And this is then introducing the notion of selection into chemical systems. For that, you need diversity. That means you need a possibility of different outcomes and different building blocks, so the system can choose some or others. And you need dynamics because, as you know, chemical reactions, they occur by collisions. If the first collision is too strong, then you are stuck and you cannot explore the thermodynamics, the hypersurface. But if the dynamics are sufficiently labile, then the system can explore. And this is why you need diversity for different building blocks and dynamics for allowing the exploration of the possibilities of the system. And I then give the name of constitutional dynamic chemistry to that, meaning by this that the constituents which form the system are dynamic. In other words, it's a chemistry of entities which are not stable. This at the beginning is something especially students didn't like. To make them work on things which are not stable. They don't like that, of course, because you are all trained to make things which are stable. But things which are not stable have new possibilities which stable entities don't have, especially when these different assemblies have the possibility to dissociate and reassociate. They can then undergo adaptation, and that opened for us this field now we are mostly pursuing, which is adaptive chemistry. Now let me now give some examples, just selected examples on cases where an external factor was used to drive the system to do something, and we'll see what. So let me, however, first point out what are the possibilities of this adaptive chemistry. Supramolecular chemistry, because, and this is what I insisted on in this dynamics, because usually the connections are labile. Now, when we see rhenium complexes, they are very strong. Rhenium complexes will not adapt. They are too strong, the bonds. So you have to have, if you want an adaptation, you have to have systems which are labile, which can sort of exchange pieces. And then, if it is on supramolecular nature, if it's intermolecular interactions, then you have a dynamic non-covalent chemistry. But you can also do then something to use this notion of dynamicity for covalent systems. Of course, covalent bonds are very strong, but there's a way to make molecular systems dynamic, to introduce in the molecule bonds which form reversibly. When a bond can form, dissociate, then it resembles, in terms of dynamics, a supramolecular system which is based on non-covalent interactions. But in this case now, covalent bonds can lead to dynamics because they can dissociate. And this is then a way of importing dynamics into covalent systems in dynamic covalent chemistry. And that is why by putting this together, dynamic non-covalent, which is natural, so to say, dynamic covalent, where you have to introduce reversible bonds, you get a sort of a field of chemistry where the constitution of the chemical object becomes dynamic. It can be supramolecular, where it's built in, so to say, or it can be molecular dynamic when you intentionally introduce reversible bonds. And this then makes possible adaptation by variation in the constitution and this adaptive chemistry. Now, what is it good for? What can you do with this? First of all, this possibility, of course, it gives a mixture. Now, we don't like to work with mixtures, except that it's very interesting to try to get mixtures which evolve in a given way, which then can adapt to different conditions. So it makes libraries. Libraries, it's just a set of compounds which interconvert. It generates dynamic diversity, and this recognition of the pieces between themselves for metal ions, since we talk about metal ions, it's the recognition of a given metal ion with a given ligand site. And this then can be used for developing search method for biologically active substances. I will just illustrate that in one slide. Implementing also dynamics in nano devices, where these metal complexes which assemble. For instance, the grids I showed, which have a different type, for instance, 9 metal ions, or the most studied we have done is 4 metal ions. You can then get devices where you can, with an STM, touch the different metal ions and oxidize or reduce them, and also for polymers. But I will not talk much about polymers. So it also means that you merge two very powerful methods. One, recombination, which gives diversity. In the older times when I did my PhD, you would say this is a mess, and you put it in a sink because you cannot do anything with it. Huh? You get a mixture. Who is interested in mixtures? You want single compounds, so you throw it away. But in fact, a mixture has a richness because it has a lot of possibilities. A mixture has possibilities which single compounds don't have. And the informatics, that's the recognition. So recognition is the information present in molecules. So this combination is quite powerful. Now, a typical reaction for introducing reversibility in covalent entities is formation of an imine. That's very trivial, but it's very important. It exists in organic chemistry. It exists, of course, in biological chemistry, the possibility of forming imines, and it is also the generation of nitrogens which can be used for metal ion binding. So you have all these features which are of interest. And let me mostly talk about imine formation and reversibility of the imine bonds in what is coming up. Now, how can you look at drug discovery? How can you lead a system like that to generate possibilities for drug discovery? If you have components of different shapes and nature, that means components, molecular pieces, bricks of different types, which have different shapes, different different atoms, but have also, in addition, a functional group here which can reversibly bind them together. So what does this give? A horrible mixture. Huh? It gives all the possible combinations here. Sorry, I don't want that yet. So all the possible combinations are accessible. It's the space of all possible combinations between the starting components. And then what do you do with it? You can throw it away because they say, okay, that's a mixture, not interesting. But you can also say there is a basic law of thermodynamics, which is called the law of mass action, or the principle of Le Chatelier, and which tells you that if you now in a mixture like that do something, thermodynamics will adjust the system. It will push it away so as to minimize, of course, to have the optimal position. And, come on, if you add to that a given receptor, and this could be an enzyme, for instance, then the enzyme will bind in this mixture the one which fits best into the cavity of the enzyme, and therefore amplify that one at the expense of the other ones. And so you have a selection of, in this mixture, the right one, this one, and this then amplifies, and you get then an amplification, so that it looked on the paper, it looks of course an ideal system, because the system is doing just the driving. The system selects and generates the best unit for binding here. Now, of course, one could discuss that when there are very, very many possibilities, then the concentration of each is lower and so on, but I haven't time to get into that. But in principle, that should work. And indeed, for instance, in order to make inhibitors for enzymes, we then looked at it by making a library of a case where we knew the answer. Of course, at the beginning, you want to have a proof of principle. So you take a system with an enzyme where you know the answer, and you set it up, and you then see whether this is what you expect is produced. And this is then sort of a way to have a new way to produce a drug. A drug is this entity which is bound by the enzyme. It can be then an enzyme inhibitor, for instance, or it can be a substrate for biological receptors. And this is sort of an adaptation. You have a mixture of exchanging things. You add in the final entity, the receptor site, the enzyme, or some biological receptor, or some molecule, like for instance concanavalin, which is a unit which binds mannose units, and then you get it. Now, I haven't time to get into that, and there are no metal ions there, so I dropped it, because we want to concentrate on what metal ions can do. So, this adaptation can depend on what is being done. It can depend on the environment. You can change the environment, add some solvents, and change the pH, a phase change between a water phase and an organic phase, a physical effector, heat, pressure, chemical effector, protons, other metal ions or other things, and even a change in shape. And this is then linked in a dynamic network, and I will come back to that in a moment. What is this chemical network which then controls the system? Let me give first some examples of cases where what happens to the system drives the formation of a given entity and selects for it. This was an early case. When you take this ligand and treat it with copper-1 in solution of acetonitrile, you get an exchanging mixture of three entities. You find by NMR that you have three systems in slow exchange, that's why you can see them, a double helix, a triangle, and a grid, a square. Okay, they exchange. Then you try to crystallize it. Usually when you do a crystallization in chemistry, you want to purify something. That means something crystallizes and the rest remains in solution. Okay? But here what happens, so it looks trivial, but it is not at all trivial. What happens here is that when you crystallize, it is the double helix which crystallizes. But as this double helix crystallizes, in the solution, all the others, they transform back to double helix. So at the end of it, you have a purification, so to say, but it's a simple purification because you get only the thing which crystallizes, which means there is an adaptation of the system to the fact that one of the pieces crystallizes and all the other ones go to that. So it's not a normal crystallization, because in normal crystallization, you crystallize, as I said, one compound and the other ones stay in solution. Here, everything crystallizes, there's nothing in solution, and everything crystallizes into one compound. Come on. So it's a solid state, the formation, the possibility to form a solid state, organized system, which drives the system to do that. Another case is the environment. If you take this ligand and add cobalt-2 to it. In nitromethane, you get a 2 times 2 grid, with a grid structure, a square. In acetonitrile, you get this thing. Why? What's going on? Simply, it's, at the beginning it was not so simple, but it was found quite quickly that in nitromethane, which is a bad ligand, NO2 is not a good ligand for metal ions, the system has to do something which stabilizes itself without the solvent doing anything. And this is the formation of here, where the system selects for the structure which it can form without intervention of the solvent. But if you're in acetonitrile is a rather good ligand, the nitrogen. So it wants to participate, and so it forces the system to leave 2 binding sites open so that 2 acetonitriles can combine. So that when you go from nitromethane to acetonitrile, in fact, it's enough to add some acetonitrile to the system. You go entirely to this pincer, this unit, which just blocks, which just binds one structure here from this one. Now, so this is one, it's a modulation of what comes out by the type of solvent you use, and maybe a change of solvent when you go from one to the other. Oxidation state also becomes important. This is the ligand here. L1 is this one with the phenyl groups. So if you take this ligand and add copper-2, you get what I just showed, this square. If you add copper-1, then, or copper-1, that means if you reduce the copper-2 to copper-1, then you get the double helix. In other words, here it's a redox state, because the coordination features of the different redox states are, of course, different, which allows you to go from one to the other. This is reversible because you can oxidize, reduce, and the system goes from a square to a double helix. Another case, to illustrate a little somewhat more complicated, when you mix this unit with this one, then they can polymerize, and they give a helical polymer. A helical polymer formed by this then replaces the pyridines at the end, and you get a helical polymer. I haven't time to go much into it, but we had been studying formation of helical polymer, helical pieces. In this case, it's even polymeric. But then you get this kind of dynamic library where you get all kinds of combinations with, let's say, the blue one is that's a red one red, and then 2 blues, reds, and so on. And this is again a mixture. But then you can add a metal ion to that, and when you add the metal ion selects, the metal ion wants to bind, and it cannot bind in a helical entity. So it forces the system to generate the ligands for making this square. So the system undergoes exchange of the pieces to produce this ligand, and this ligand can form this square. So this is for metal ions. Now I will give you some organic chemistry examples, and we come back, you will see there will be many metal ions left to study. That case is the following one. You have 2 units which look the same. They're not exactly the same, of course. You have a core, which is carbazole. Carbazole is a rigid core, very hydrophobic. It doesn't want to touch water. To make it hydrophobic, you can attach a chain, hexaglyme chain, and now these things become soluble in water. But they don't like, one piece doesn't like water. The other one piece likes water. Now, when you mix those two together, what happens is, we studied that in detail, is you get a ligand, you get a polymerization with formation of a helical rod. Why? You make a polymer, but the polymer is under the influence of the hydrophobic effects. That means the system wants to minimize contact between water and hydrophobic residues. So it wraps around, extends the hexaglyme. I haven't put them here, but these long chains, these hexaglyme chains, they stick out of this rod. So this thing is soluble in water because these things stick out and are possible to dissolve in water, but the center is containing the pieces which are hydrophobic, so as to minimize the contact with water. So you say, okay, now this is an interesting, it's a very interesting polymer because it's one of those pieces which have an inverse correlation with temperature. Usually you would say, if you heat, you go to pieces. No, this gets bigger. When you heat, it gets bigger and bigger because of the hydrophobic effects. This is well known also in biology. But then we can now ask the system to make a choice. Very simply, you add now this system, you say, okay, so what? This is so different, the same thing. Not the same thing. This has a benzene ring, and this has a carbazole. So the benzene ring is a smaller piece, it's hydrophobic, but it's less hydrophobic than the carbazole. And so what the system is doing is nothing. That means it does not incorporate in the polymerization this smaller unit, it just does the same. But how can you confirm that? If my story about the effect of hydrophobic forces is correct, then you can take, this is a water solution, you can add an organic solvent more and more and more, and progressively go from pure water to more and more organic. And then the system should lose the selectivity, which is exactly what happens. In other words, the more you add acetonitrile, the less the hydrophobic effects are strong, and you lose the selectivity. And at 80% acetonitrile in water, you have a random incorporation of this and this. That shows that indeed it's a system which is under the control of hydrophobic effects of the medium. The component selection shows that it's an adaptation to the aqueous environment or to the mixed environment, water, acetonitrile. What we did with the group of Paulo Samori in our institute had to do with again selection by a surface. Take this aldehyde, long chain aldehyde, and 3 diamines with 2 carbons, 6 CH2s or 12 CH2s between the nitrogens. And this is a phenyloctane, is a sort of a common solvent for these things for people who do this deposition on surfaces and then do STM on them, imaging on them. When you look at, when you look at the solution by NMR, what do you see? You see a mixture. And even worse, you see a mixture of monoimines and a little bit of bisimines. So it's okay, it's a mixture. But then you put the drop on the surface and you let it deposit. Then it gets very interesting. What you get is the deposition of only one compound. The compound which is a bisimine and the C12. In other words, among this mixture, there's one of them which gives the best assembly on the surface, and that one drives the system to make itself. And what it shows is that the simple adsorption, the fact that let's say, I couldn't even say the fact that the system can lead to a stable adsorption of the bisimine with C12, makes it generate that and only that. So the simple adsorption on the surface drives the reaction to form a bisimine and not simply a monoimine, and it drives the component selection to the C12, only the C12 bisimine. This means there is a adaptation to the surface adsorption, which indicates that a simple deposition on a surface of a dynamic system can drive the system to do something which is selective. And so the self-organization drives the selection, and one may even say, now this is pushing it a bit, I realize, that is, in the origin of life, complexification of matter needs thermodynamics. We are all depending on thermodynamics, otherwise it would not exist. And it drives, no, of course, I don't claim that this thing has anything to do with the compound which existed at the beginning of complexification. But what it shows is that if you have a starting mixture in presence of a case of a surface which can lead to the deposition of one of them, of these mixtures, that one will form, and the other ones will not form, or that one will be preferred by the simple fact that you can generate an organized depot. An organized, in this case, it's of course, you see, it's very nicely organized, so it's quite obvious that that's the one which wants to form. Now, I have to hurry up. I will probably just give you the results of these things, and then I drop the ones which can illustrate that you have. Then I can talk about it if you ask questions. Start with this compound here. This is a W, so to say, and it can then also undergo, if you have here the groups here, the red ones are functional groups. This can be aldehydes, and these ones could be amines. So if you mix two different diamines, you get a polymer. You get a mixture, nothing very interesting, something like that. But then you can act on the system in the following way. First of all, you add a metal ion. The metal ion will transform W into a U because it binds the metal ion in a unit which can do a complexation. Now, the two groups are now totally different. And now this can be a selection of one of those things if that one has just the right shape or the distance of the groups which lead to this formation of a macrocycle. So that is a metallo selection. On the other hand, you can shine light. When you shine light, then you make a trans to cis conversion, which gives one which is also a cis compound, but where the distance between the two is not the same, and then you get a selection of another one. So this system has three stages. The initial stage, which is a mixture, one stage which leads to selection by a metal ion, and the other one to selection by light, by a change in conformation. Let me just illustrate that. Okay, this I forget it. Now, something important is that these two states are at equilibrium. So these are equilibrium states. But, and this is the easiest way, you know how nowadays a very important topic is to generate out of equilibrium states. And the easy way, a comparatively easy way to generate out of equilibrium states is light. Light can generate something which is unstable thermodynamically, it goes to the excited state, and a transform goes to a cis form, and that one is out of equilibrium, so this one is an out of equilibrium state. But let me illustrate that one by real molecules. So we have this dialdehyde. We mix this dialdehyde with four possible diamines. This one, this one, this one, and this one. And what happens then is that you have no selection because you just get the mixture of all kinds of combinations, polymerizations, and so on. Now, if you, on the other hand, I pushed the wrong button. If on the other hand you add lead to this, then it bends around, positions the aldehydes in different distances, and now the presence of the lead also selects for the one which has an oxygen here, because this also can bind to the lead ion, and therefore, out of this, you have now one compound only, which is this macrocycle with a lead ion inside, and the other ones are just free out. If you do this transformation, the photochemical transformation, now, as I said earlier, these two aldehydes are positioned differently. And now you get interaction with the C7, with this one, forming now a selection of this. So the system has 3 levels of selection. In fact, the first one is not selection. One level, which is here, no selection. One level where you have metallo-selection, and one level where you have photo-selection, where the system generates something different depending on what is imposed on it. And you can do this, you can interconvert those directly just by adding lead to this thing, you get that, and by shining light on this system, you get that. Okay? That is just what I showed you. Now, let's analyze those systems of interconverting entities. Suppose you have 2 aldehydes and 2 amines, or let's say in marginal terms, a compound A, a compound of same type but somewhat different A prime, of B and B prime. And the A's can react with the B's, but not the A's with the A's and the B's with the B's. So you can make 4 combinations. A, B, A, B prime, A prime, B, and A prime, B prime. This is 4. Now this is a network, because all these 4, they talk to each other, because if something happens to one of the components, the others will know it. So what is the network? It's simply a square. Pardon. It's simply a square where this 2-dimensional network is consisting of the 4 constituents located at the corners of a square. AB, AB prime, A prime B prime, A prime B. Now, if you have a method for increasing, for instance, AB, the system is contained, it's closed. You have only a given amount of A's and B's, and A primes and B primes. So, if you have a way to, we will see that later, but if you have a way to increase one of them. For instance, if you increase AB, how can the system increase it? It can only do so by taking this A of AB prime and this B of A prime B. Then AB can form, you can form more in AB in the system. But if you do so, then A prime and B prime are released, which can form more A prime B prime. So this is a very simple case, but which illustrates what can happen in a complex interchanging system. AB around it, on the edges of the square, the constituent which are linked share a component. AB shares A with AB prime and B with A prime B. So these are antagonists. If AB increases, the other 2 decrease, must decrease. But this is all right, but not so interesting. What is very interesting is the fact that if you do so, as I indicated, then A prime B prime must increase. In other words, on the diagonal, you have agonists. So on the edges, you have antagonists, and the diagonals, you have agonists. They do not share a common component. AB has nothing in common with A prime B prime. Now this has a very interesting consequence. First of all, you can modulate it by changing the concentrations or by increasing one or the other one by some external effect. And you have a process which I feel is very important, which is you may call agonist amplification. When 2 in a complex, this is a rather non-complex one, but it illustrates the principle. When you have a mixture of this kind, if entities in this mixture do not share a component, then if one increases, it liberates some other things which can form the other one and go the same way. In other words, the fittest amplifies also the unfittest. That's a rather strange concept, huh? But the best one for doing something amplifies also the worst one for doing that thing, but maybe it can do something else. And so this is sort of adaptive network, and let me illustrate that by metal complexes. So I come back to metals now. This is trivial, huh? An undergraduate student can do this. You take A, pyridinaldehyde, you take A prime, benzaldehyde, you take this hydrazate on benzene, you take the same one with a methyl group. Okay, all right, what is this? What is doing? Of course, it gives 4 constituents. It gives AB, AB prime, A prime B, and A prime B prime. Okay, so what? So what? Pardon, the wrong one again. But voila. Now we can drive this system. These are the 4 constituents which we can generate in this library I just indicated. And now you add the metal ion. What is the metal ion doing? The metal ion will try to bind to one of those 4. And it will, of course, bind to the best ligand. Which is the best ligand? You can see that here N, O, not so bad. If in addition you add a base or a weak base which can ionize the H, then you will have probably a strong ligand. And indeed, when you add a metal ion, you get, as a result, something which has, which is this complex here, and where the, what is this one doing here? That shouldn't be here. And one which cannot bind the metal ion. Oh no, sorry, it's correct, yeah. So, when you add zinc, that is what has happened. You start with your network, where you have more or less 25% of each. You add the zinc. The effector is M, this metal ion. It amplifies AB, and it amplifies A prime B prime. Of course, A prime B prime is not very good for binding metal ions. It's the worst one of the 4. And this is an adaptation of the system to the fact that you added a substance which pushes it in that way. Pardon. So you have agonist amplification again. I insist on that because I feel it's a very important property, that the fittest for binding zinc amplifies the unfittest for that, the one which does not bind zinc very much, in fact, not at all. Yeah, then, okay, let me show you a much more complicated case, but which has a lot of information of interest. Now we go to 3 times 3. That's a network with 9 possibilities. Okay? So, you mix them. What you get? Something not interesting. Just a mixture and nothing interesting. You see, you have some things form, they combine together, a lot of free A4, which doesn't do anything, free D4, which doesn't do anything. Okay, so first reaction is throw it away, it's no good. Then you add copper 1. It's even worse. Copper 1 can be oxidized to copper 2 if you have a good ligand for copper 2. And aminoquinoline, this aminoquinoline here, is a very good ligand for copper 2. So when you add copper 2, the whole system goes to hell. It just, the system is oxidized by air, because we are not under controlled atmosphere, and the system is just destroyed. Okay. Then you say, finished. Bad experiment. But then you start by adding iron. The same thing. You add iron, and then what happens is, of course, iron likes aminoquinoline. So you make the complex aminoquinoline with iron. That means the one, you see this unit here, this is the aminoquinoline, and here you have the pyridinaldehyde. So, now so this is the first thing which forms. Iron binds to that ligand, that combination. In doing so, of course, you have now things left in this network, in this 3 by 3 network. Now you amplify not simply one constituent, but a square. In other words, the addition of iron leads to the formation of the complex with the aminoquinoline, with the ligand aminoquinoline and pyridinaldehyde, and it leaves the other ones free, but those form a 2 by 2 network, so you have an amplification here. And now you add copper 1. You get a very simple system. Copper 1 now is free to do what it wants to do because the aminoquinoline has been removed, and now it amplifies one diagonal in this network here. It even reverses the diagonal. This is what was left. So if you add copper 1, you get now a network which at the beginning was very complicated, which now is very simple. Just one diagonal where this is the complex of iron, this is the complex of copper, and this is what is left, which also makes just one of the constituents of the diagonal. Now, what can we deduce from that? Okay, this can also be done directly without a sequence, but the sequence was important. First of all, it shows you that you have a two-level agonistic amplification. The first one is the iron, and the agonist here is a square, is a network by itself. This is one entity being an agonist to a network, a 2x2 network. That's number one. Then you have a conditional response. Only if you first start with iron and then copper do you get the result. Otherwise, it doesn't work. So that is often, this is something which suggests that when one does chemistry in complex systems, the sequence of addition becomes very important. Then, another point which is interesting is that adding one more entity, one more ion, rather than making the system more complicated, makes it simpler. The fact that you have an increase in complexity leads to a simpler output. In other words, an increase in complexity leads by dynamic competition to a simpler output. So complexity, despite the system is more complex, the output is simpler. And this is one case only. We have other cases like that. In organic chemistry, it works also. Finally, you have step 1, which is adaptation to the first effect. It's just a summary. Step 2, adaptation to the second effector. And you have this is also sort of important. That's a step, it's okay. It's pushing it a bit here, I realize. But adaptation is the case where the system adapts. You remove the effector, it will go back. Okay? But evolution, that is adapting and keeping the information and going a second step. So here, this is what you have. The first step, the iron is conserved, and then the copper can go one step further, so the system evolves from one stage to another one. Let me finish with this one. Yes, this is now one which is a bit more complicated. It has to do with a biological system which uses metal ion to organize itself. So, what is well known is that guanine can form a supramolecular macrocycle. This is well known, biochemists know that, as known since the 1950s. You form a guanine quartet, a G quartet. And these G quartets are stabilized by metal ions, and this is just an example of what they do. They make plateaus of quartets, and the metal ions are between those and stuck the whole thing together, and give a gel. Note, a gel. I come back to to that. And this is just to show that it works also with a modified compound. We have guanosine transformed into the 5-hydrazide here, guanosine hydrazide. And of course, it does the same as the normal guanosine. It forms a supramolecular macrocycle with this guanosine hydrazide. Here is a picture of the gel, and this is showing the gel. Now, a gel is an organized state compared to a solution. A solution is a solution, everything moves. A gel, something does not move. Otherwise, it would not be a gel. And the gel has a melting point. And the higher the melting point, the more organized it is. So, then you can do the following. Here is a hydrazide, which was introduced because there is an NH2. So because of this NH2, we can do something on that position. Now, the system has 3 types of dynamics. First of all, it has supramolecular non-covalent dynamics because it can form a macrocycle by hydrogen bonding. This is the classical thing, which is well known for 70 years. In fact, this is at the end of our chromosomes, and the 2 ladies who got the Nobel Prize for the telomeres, the end of the chromosomes, they form tetramers, guanine tetramers at the end of the chromosomes. But that's a whole different story, a big story. So this entity then can bind metal ions, which are reversibly bound. So this is now a supramolecular non-covalent inorganic dynamic part. And finally, you can decorate these units by condensation with an aldehyde, here 4 aldehydes, and this is a molecular covalent dynamics because now you have imine formation at on the outside of this superposition of supramolecular quartets. So these are the aldehydes we used. And in given conditions, of course, since you work with gels, the conditions are important. The temperature is important, the concentration is important, but you fix that. You have a given concentration and a given temperature fixed. Now, I don't go into the details, but with different aldehydes, like the ones shown here, for these sulfonates, for the same compound, that means when you begin to react this unit with these aldehydes, here you get in conditions where this was giving a gel, the condensation with these aldehydes leads to a solution. It dissolves the gel. Okay? These 2 give what you may call a better gel, especially pyridoxal phosphate, which is the cofactor in transaminase enzymes. So that was quite interesting. A better gel meaning that the gel formed by reacting this system with the pyridoxal phosphate has a higher melting point than the others. So the formation of a cell, a sol or a gel, depends on the residue which is attached. And now we will ask the system to tell us something. We start with a network with 4 components. One is the hydrazide of guanine, the guanosine hydrazide. Okay? That's the one which can form G quartet. Here, that's the hydrazide of serine. Serine hydrazide does not form a gel. It does not form a supramolecular ring, nothing like that. These are 2 aldehydes. That one is one which leads to a less good gel, which gives a solution, as we have seen, whereas this one gives a better gel. So what is the system doing? You have now these 4 units, and now the system has to choose something. You know the solution, I guess. What happens is, of course, that in a system like that, you can, that's first, how can you analyze it? Of course, by NMR. What is the NMR telling you? You have a gel, but the gel is something sticky and water between these things which are sticky. So everything that is in the water can move, so that has sharp signals. And everything that is in the gel is very broad because it cannot move. It's a gel. It's like a confiture. So what you get is you can measure by NMR the presence of these 4 constituents. And from that you deduce that what is left, because you don't see the other one, but of course you know what it is because you can integrate that. What is left, the gel, contains this. So the gel is formed by a G quartet with the aldehydes which give the best gel. Okay? So AB is amplified as a consequence, A prime, B prime, the agonist is also amplified. So these are the results, AB about 40%, A prime, B prime about 40%. And the other ones are the antagonists, they are only about 10%. Okay? Which means there is amplification of the constituent AB, which leads to gel formation and to the best gel in these conditions, whereas the other ones remain in the solution. You can even determine the driving force of the gel simply by the ratio of the way you have perturbed the system. It's about 1 kilocalorie. So there's a selection occurring under the, let's say, the driving force of organization. That's very important in chemistry because it means that when something can organize and can, by dynamic ways, make the system which is better organized, it will do it. In other words, organization drives more organization. That's also very important in the evolution of complex matter. And this is just repeating the same thing, but by using the network representation. That's what you get here. And to its adaptation, selection, adaptation under self-organization pressure. There's a self-organization drives the system to make self-organization. And so this, again, agonist amplification. And this is also, I think, very important for prebiotics. Again, it's not this type of system which existed at the beginning of more and more complex states of matter. But the fact that the presence of organization in a system is the endpoint. It will generate these entities which lead to that organization. And I can represent it. Oh yeah, that's okay. I mean, because of time, I will drop that. That's an interesting case where you can distribute between two phases, but let me leave that out. This is something this is done by a Ukrainian co-worker, Artem Osipenko. So this is a case where we have a two-phase system. Two-phase system where we have a mixture of different ligands distributing between two phases, chloroform and water. Then you add an effector to the water phase on top. It happens to occur the water is on top because chloroform is heavier. And this generates a different distribution of what was present initially here. This is the initial distribution. You add one metal ion, for instance, then you get a dynamic fingerprint. You add another metal ion, you get another dynamic fingerprint. So if you were a Maxwell diamond sitting on the bottom here, you sit there, you don't know what is happening on top, but you look what comes down from the surface. Depending on what comes down, you know what has been added. You know that it may be iron, it may be cobalt, it may be copper, it may be nickel. And this is what I don't want to get into it. That is what you get when you take these four constituents and you add manganese, iron, or cobalt, or nickel, or copper 1, or copper 2, or zinc, or cadmium, or lead, or palladium. And this is characteristic of the metal ion. So the distribution tells you what has been done. Now this is for us a little bit strange because I have spent much time on molecular recognition. Here you have no recognition anymore. The information is in a distribution and not in an entity. In biology, an enzyme binds a given substrate. And so the information is the log and key, a la Emil Fischer, log and key combination. But here, the information is in a distribution. From the distribution, from the fingerprint, you know what happens. But it's not selective. It's just a distribution. Okay. Yeah, okay. Yeah, when it's two phases, in fact, it's not a square anymore. It's a square prism. But let me not insist on that in view of the time, because, wait a minute. No, this is, yeah. I should say something on that. Should I not? Let me see what yeah, this is just, yeah, okay. No, what I Okay, what this shows is that the system can also learn something and retain the information. Maybe it's interesting to show you quickly. I go back. I was a bit, usually I'm too long, I know that. So, if you have 4 pieces, A prime, B prime, and you combine them, and you see this cavity have different shapes, okay? Now, this is the system in equilibrium. Now we add, under kinetic control, that means kinetics are slow now, not fast, you want them slow, you will see why. You add metal ion which wants to be hexacoordinate, octahedral, 6 coordinations. And then, of course, it will bind to this one which has a hole, which is hexacoordination. So you change your system by amplifying these two with agonist amplification, and this one are down-regulated. Now, you add another ligand, a better one, it removes this, okay? And what is left is now a prepared system, a memory system, because this to here takes time. It goes slowly. And once it is done, you can remove the unit which has led to the imprinting, and the system will stay. Of course, it will slowly go to equilibrium, but it will keep this information. So if you now add to it the same thing which you have removed, it will immediately know it, because it recalls the system is prepared. So you can start with a dynamic system, lead it, force it to modify itself, then can remove what has been used for imprinting, and this then leads a system which is out of equilibrium, which wants to go back to the equilibrium state, but it's very, very slow. So that if the same object as the one which initially has been used to create this state is again introduced, it will immediately be recognized. So without going, you can do it with another ion, but what is important is this. These are out of equilibrium systems, that's memory. Memory is out of equilibrium. When we retain something, we are out of equilibrium. We are out of equilibrium, we have no memory. So it's an out of equilibrium system. And we are quite a lot working now on this to make out of equilibrium systems which keep the information for some time, of course. So this is just a realization, so I don't want to get into it. And so, what are the lessons we get out of this? First, you have constitutional dynamic networks. You have a response to a sequence of agents, and the sequence is very important. You have self-organization, which drives constitutional adaptation. Agonist amplification is a very important feature, where the fittest amplifies also the unfittest. An increase in complexity can lead to a simpler system and not to a more complicated one. The information can be contained in a distribution and not in a given fitting together for lock and the key. And of course, you can generate out of equilibrium systems. Okay, I am at the end. I'm sorry, it's a bit over time. Not too much, I think, but thank you very much. In my defense, I can say that is what happens in cells. In cells, when something happens somewhere, the others know what is going on. Huh? So they talk to each other all the time. But this is much simpler than a cell.
Thank you very much for this super lecture, as always. And now it's time for some questions. Anybody question?
You still feel like at the end of the day, huh?
I don't know. Well, may have one. Do you need rigidity for this constitutional framework? I mean,
Rigidity.
Rigidity is important because you are using simple components.
Yes. Rigidity is not exactly the thing. It's just, at the end, slow kinetics. Usually you want things to go fast. And this is what we're looking for. But if you want to have a system which keeps information, then you want a slow reaction. And you know, for chemists, this is the reason also why a condensation with an amine, with a carbonyl, is interesting. Amines are different ones. Aliphatic amines and carbonyl, they go fast together and they go away again, in water solution, of course. Very fast exchange. Then you go to aromatic amines, it's already slower. Then you go to hydroxides, then CONH, NH2, they make also imine, C and double bonds, but they're even more slow. Then you go to hydrazines and carbonate, that means hydrozones. Hydrozones are even slower. And the slowest are oximes. Hydroxylamine with a carbonyl, they give oximes, but oximes are very slow. So you have a whole gradation. That's why imines, the C and double bonds are very interesting. You have a whole section, a whole gradation of rates of exchange. And oximes are by far the slowest.
Thank you. Any more questions, comments? No? Please. Mr. President.
Prof, linked the evolution with the organization. It's not a chemical question, but it's more a philosophical question. What about the fact of linking? You talked about the self-organization, so we saw that it works. With what we study since the beginning about the disorder of our system, I don't want to talk about the entropy. I repeat, it's more philosophical than chemical, but, they teach us, you know what, the disorder is always increasing, but we see that nature organizes in the end.
Yeah. This is a question which is an important one. It gets often asked. Let's say, what about entropy?
I didn't talk about that, but
everybody has this question, yeah? What about entropy? It's not entropy that drives the world. It's free energy, delta G. Otherwise, there would be no molecules. You take two hydrogen atoms. In order to make a hydrogen molecule, you have to bring them together. So you start with 3 and 3 degrees of translation. 6 degrees of translation. And you make an entity which is only 3. So you lose entropy. But why can you lose entropy? Because the bond makes it possible. So in chemicals, the evolution of a chemical system is driven by delta G. And delta G has to become lower and lower. So it's very important. And in an open system, of course, the universe always increases in entropy. But you have a closed system. It's delta G which drives it. Now, I am very fascinated by this question that in fact, it's like if the universe knew that at the end there is organization. The fact that you can get organization drives the system to make organization. I'm convinced that is because we are here. Otherwise, we would not be here. No, our universe is such that organization is sort of let's say, a cosmic imperative, I may put it. You asked a philosophical question. It's a cosmic imperative. Life is not an accident. Life is a result of the thermodynamics of our universe. There are many interesting questions behind that, which you usually leave for dinner after a glass of wine. Thank you for the question.
Let's thank Jean-Marie Lehn again. Thank you very much for coming.